So our content this week focuses on strain transformations. Earlier in the quarter, we've already done stress transformations, and we remember that by 3D Hooke's law, strain and stress relate to each other. So this transformation is going to be extremely similar in procedure, just a few slight variations and differences. Right? Why would strain transformations be important? And so the state of strain is something that can be measured. So as we'll end up having a lot of problems where strain gauges will be put on free surfaces. So generally we're dealing with a plane stress problem. And whenever we have a surface that we can put a strain gauge on, but measuring the strain on a surface will then relate back to the stress on the surface, which can ultimately lead back to understanding failure criterion and how close the material is to yielding by von Mises or Tresca. So just a modest amount of setup. It'll be quite similar to what we've done before. So we've got normal strains and subscripts that deal with XX, YY. Prime is going to be in the transform direction or the rotated direction. YY prime, ZZ prime. Also the principal strains can be calculated. Those will relate to the principal stresses. And so these normal strains will be positive for elongation. So it's very similar to positive for tensile stress. For shear strain, also known as gamma, right, this angle, and this is related to the coordinates x and y. So if angle AOB, where we have a shear stress that's applied to a material and a shear strain results, and so if that angle decreases, then gamma is going to be positive, and that's going to also relate back to tau xy is equal to g times gamma xy. So positive shear stress is going to relate to positive shear strain, right? In our notation, this is also sigma xy is equal to g times gamma xy. So our derivation is going to go actually pretty quickly here. Just a couple things to lay out first. And just like we did with the stress transformation, we're going to relate the action on a certain axis to then action on a different set of axes, but those are going to be related to each other. So for stress transformation, we ended up using equilibrium. Here, when we're dealing with strains, we're going to have to use kinematics. So sort of one last thing here to make sure we lay out, and you'll see this on your equation sheet as well, is that the gamma, or the shear strain, it is related to epsilon xy. So those are slightly different. And the reason why they're slightly different is we're going to take gamma and we're going to split the difference in between there. And so as you remember from equilibrium, tau xy equals tau yx. Right? And that's essentially the rule is once we know the shear stress on one face, we can draw it on all four faces. And so it's because of equilibrium that those are that those have to be true. So epsilon xy is going to equal epsilon yx. And so we're going to take gamma and we're going to rotate it and split the difference between those two. So you see it twice here, both on the prime axes and then also over here on the xy axes. So just something to keep in mind, that epsilon xy is going to equal gamma xy over 2. So to begin our kinematic relationship, we're just going to start with a deformation relationship. So we've got our x, y axes, which perhaps would be the initial axes. Generally, we think of them that way, as some initial state, some initial axes that have been set up on the problem. We're interested then in finding the strains on a rotated axis, and that's because this may be the principal axis or the maximum shear strain axis or any rotation, right, through an angle theta. So the deformation relationship is going to relate dx to dx prime. So we've got just by geometry that dx is equal to dx prime times cosine theta. And then also dy is equal to dx prime times sine theta. So we're going to continuously use these relationships as we work through the kinematics. So just as our summary here, right, dx prime relates to dx and dy through this angle theta. So we're just going to track our three different strains, two normal strains and then one shear strain. So let's take a look here when epsilon xx occurs. So there's our dx now has changed lengths. It now has an additional epsilon x times dx value. And what we're going to end up tracking is this red line. So we're going to take that answer on the x-axis and we're going to project it or put it onto the prime axes. So in the x prime direction, we'd have epsilon x dx times cosine theta. We'd also have another one in the y prime direction we'll kind of keep track of. So it's going to be epsilon x dx sine theta. So we're just going to track that. So the movement in the x prime direction, so right there would be delta x prime from contribution 1, where contribution 1 is going to be epsilon x. So again, just all by kinematics, all just geometry. So then just plug in the value that we had for dx, right, that we got from the before deformation relationship. And so there would be our answer for movement in the x prime direction. So we've got to do this 2 more times here. So we're going to now track movement, right, or strain in the y direction. So something that would be initially length dy would now have an additional length epsilon y times dy. And so let's just track these values in here. And what we're interested in is really this one right there. So that's going to be epsilon y dy times sine theta. And so we're going to track the projection over here on the x prime axis. So there's our value for delta x prime 2, right, where we're talking about epsilon yy. And then we're just going to plug in our relationship for dy that we have. And so there's our contribution from epsilon yy. So the last one would be the contribution from shear strain. So we'll get in here a little bit tighter at the kinematics. Little more challenging, but again, what we're tracking is the red line. So we want to find the contribution of gamma, and gamma would create gamma xy times dy. All right, we're using extremely small angles here, and so the projection onto the x prime axis would be gamma xy dy times just the directional cosine, and that'll give us our last expression. So delta x prime 3, and we just plug in the expression for dy in terms of dx prime. So we're just going to use superposition. We're going to add those 3 contributions. All right, we add them together. Those will be the total deflection, right, or movement in the x prime direction. So we'd end up with, just kind of writing this back out, epsilon xx dx prime cosine squared theta plus epsilon yy dx prime sine squared theta. And then the last contribution was the one we just did. It would be gamma xy dx prime sine theta cosine theta. So to end up with an expression for the strain in the x prime direction, we're going to take both sides of this equation and multiply by 1 over dx prime. Right, that would then give us the change in length over the original length, giving us epsilon. The dx primes would all cancel. And so then we just got a little bit of math to do. And you'll end up seeing this equation, again, a little bit later, but we'll do a little double angles, and we'll end up with an equation that really looks exactly the same as the stress equation transformation. So you see elements of twice the angle. You see, again, we'll show this more on Mohr circle. This is going to be epsilon average, right? The two normal strains divided by 2. And so we'd have a similar procedure to come up with the equation for epsilon yy prime. So the last one gets real tricky when we come up with the gamma x prime y prime, the transformed gamma calculation. But let's just kind of look at the kinematics here. So we're going to deal with a delta x prime divided by dx prime. That would give us an angle in here, again for small angles. That would give us an angle alpha, right, where the tangent is approximately equal to the angle for something very small. Right, we'd have another angle beta, which would be tracking delta x prime, which would be that right there, delta x prime, divided by dy prime. That would be another angle beta. And so we have a shear strain when alpha minus beta, well, actually when it's not equal to 0. So that is the measure of the change in angle. So there's a measure alpha and beta. So we got a little bit of math, again, to work through there. And we're just going to kind of jump to the final equation. So this is right off your equation sheet. So you end up with an equation for strain, right? Normal strain on the x prime axis. You've got normal strain on the y prime axis, which is going to be perpendicular to the x prime. And then the shear strain, which works between. And you also see this gamma over 2 that shows up. So let's just kind of look at the big picture here. Right, what do we need here to calculate transform strains? We need 3 initial strains. Epsilon xx, epsilon yy, and a gamma xy. And we need an angle theta. So this is exactly the same thing we have with the stress transformation needs here. Any 3 initial strains plus an angle will give us an answer on a rotated axis system. And so we're going to have some good problems that deal with initial strains. And we also know the initial strains relate to the initial stresses. So those will start coming up in these problems as well. So the other thing we can leverage is Mohr circle for strain. And then on the horizontal axis, we're going to put normal strain. On the vertical axis, we're going to put gamma over 2, again calling clockwise positive, very similar to what we do in Mohr circle for stress. And so it's an extremely similar procedure. It's actually going to be exactly the same. We're going to plot the x face and the y face strains. Right, that'll get us going. Right, our 2 initial points. Going to connect those 2 points, finding the center and the radius of the circle, and then we can do any sort of movement on that circle. Right, the other thing to remember is that twice the angle on Mohr's circle is what it is in real life. So that's where the 2 theta manifests itself on Mohr's circle. So those are just sort of a couple of the things to remember. The other thing that jumps out is that this is gamma over 2, and so we'll be used to that after a couple example problems. And so here's a pressure vessel picture, and really what happens is you end up with calculations that are very challenging to do with a state of stress example. Obviously, we use St. Venant's principle in all our calculations, so we stay away from the area of applied loads, connections, place we stay away from. And so to be able to help you calculate states of stress that would be in areas close to supports, close to applied loads, you can use strain gauges. And so here's the exact look that we've got for Mohr circle. Again, we're just going to plot 2 initial axes. Right, this is going to give us 2 points. We'll be able to come up with the center of the circle, the radius of the circle, and then we'll be able to rotate through any angle theta that we might be interested. Here we'd end up with epsilon max, epsilon minimum. We hold off on doing the 1, 2, 3 until we know what's going on with epsilon zz, right, what its value is. Up here on the top, this would be gamma over 2 max. Right, just remember this is going to be gamma over 2 with clockwise positive. So all these Mohr circle equations come in very nicely for us. And our ability to do these problems, right, then we also use our pink theta, that initial, any initial angle, and then from that we just run some theta games to solve for theta p, theta s, or to do a prescribed rotation. Kind of look at a couple more pictures here. There's our Mohr circle for strain again. Right, some of the values, right? Epsilon average would be right in the middle. There's the look at gamma and the relationship of why we use gamma over 2, dealing with shear stress and shear strain. And so this is just on your equation sheet, you'll start to see some relationships. Sometimes it'll show up as an epsilon, or other times it'll show up as a gamma. So there's a relationship between those. Here it would be in 3D. Dealing with the 3 principal strains. So once we know our Mohr circle in 3 dimensions, then we can deal with all of our 3 principal strains. Those principal strains relate to principal stresses. And we've seen those relationships on 3D Hooke's law. So a couple problems, problem types. A new problem type that shows up would be what's called a plane strain problem. So that's where we know that the strain in the z direction is equal to 0. A dam would be an example where z is on the axis on the arch of the dam. We would be designing a dam that had 0 strain in that direction. And so the reason why the strain would be held to 0 is because there's, right, some application of sigma zz is most likely present. So again, just keeping in mind that is what we call a plane strain. So you want to read these problems very carefully. Sometimes it'll tell you if it's a plane strain or a plane stress problem. So remembering what our plane stress is, that sigma zz is equal to 0. That's our free surface. And because it's free, epsilon zz must be calculated. And we'll go through how we do that using the equation sheet. And we'll eventually come up with a relationship with strain in the z direction will relate back to the strain x and y in a plane stress problem.